Slides are visible?
Yes, sir. Yes, sir. It is visible.
Okay, so let's start. So we'll start a new topic today. File system video lectures I have already forwarded to you. You can go through them, and if you have any issues, you can always ask. So I'll be having one doubt class where I will ask some questions regarding file systems, maybe after Diwali holidays, and then we'll cover the file system again in detail. Fine. So memory management, most of the things you might have covered in your computer organization course of memory management. There was a separate topic over there. But here we'll see memory management from the operating system perspective. Basics, when a system boots up, when you boot up your system immediately after the boot up, the RAM would contain memory image of kernel executable. So your kernel means your most important part of operating system. That particular executable uh, will be loaded in RAM first up. How system boots up, you should be knowing. But after system boots up, memory image of kernel executable is loaded into RAM in low memory addresses starting from byte 0. And over time, the kernel allocates rest of the memory to various running processes. For any process to execute on CPU, this we know that if you want to execute any process on CPU, for that process, instructions and data must be available in main memory. Means if you want to run or execute any process, that has to be brought back from hard disk to the main memory first. Execution of process generates several requests for memory reads and writes, and this is the duty of memory subsystem of operating system to efficiently handle these requests. The design issues must be less delay and more availability and things like that. And this is what we are going to see in this lecture. The operating system will ensure that running process reside in memory as far as possible, but this is not always possible. When your system runs low on memory, the running process also may have to be moved back to the hard disk, swapped out to the hard disk. And swapping process which is out would be kind of blocked but in suspended state. A process which is blocked on some IO and it is remaining in main memory, that is known as blocked state. But when there are many number of blocked processes and all are waiting for some IO, so that ready queue would be full. So you may need to swap out some running processes also. And when there is a need of that process may be swapped in. So this particular thing keeps on happening, swapping in and swapping out, because your main memory size is always smaller than your secondary storage. And with the virtue of virtual memory, you provide an illusion that you have lots of RAM and very large programs or very large processes can be executed. But in reality, that is not the case. We have 4 GB, 8 GB, 16 GB of main memory. Uh, but our processes, like operating system itself, is nowadays, if you have a full operating system, is more than 15 GB, 16 GB. So operating system itself is not coming fully in main memory from the scratch. So you just bring back the most important routines of operating system known as kernel, and then when kernel executes, it calls another processes which are in hard disk. They are swapped in, and then memory, if memory is less, they are swapped out. New process will be swapped in, and things go on like this. Swapping processes out leads to performance penalty, and this you need to avoid as far as possible, because in your computer system, the slowest device are your peripheral device, like your keyboard, printer, monitor, your hard disk, these are the slowest device. So if you are throwing any process back into hard disk, next time if you want to run it, that's a lots of penalty, lots of performance penalty. So there is always a trade-off that how much time you have to bring the process, you have to keep the process in memory. If that memory is needed for any other important process, interactive process, because that process has been double clicked, so you need to free up the memory, bring the process in from hard disk to main memory, and these things keep on happening. Logical address, as we have already discussed, the memory address generated by CPU are called logical addresses. Logical virtual address space of process, we have discussed a lot on this, ranges from 0 to maximum value. It depends upon the CPU organization or architecture. Like if you have a 32-bit machine, the logical address would be of 4 GB. Code and data in program executable are assigned logical addresses in this space by compiler. Compiler always generates logical addresses, thinking that whole 4 GB of memory is for this program only. So you can start from any 0 or any other location from 0 to 4 GB. That particular logical address or virtual address is for that process. And compiler generates addresses in this area. Physical address, addresses used by actual memory hardware to locate information are called physical address. The physical address space of system spans from 0 to some maximum value determined by how much RAM the machine has. So if it is having 8 GB of RAM, then from 0 to some 8 GB. Now this is what is the interesting and important aspect. The mapping of logical address of a process to a physical address. That is done by some address translation maps or ATMs. So we'll be seeing that thing in detail. But before moving ahead, let's discuss something of importance. So, and if anybody can answer this. What is happening? This is a CPU. So, and a process is executing. It's executing. Program is executing. So CPU has a program counter register, as we all know. Fine. And program counter will gives you the address of next instruction to be fetched. Program counter gives this address. CPU generates logical address. Now, many of you might recall that between CPU and main memory, between CPU and main memory or RAM, there are L1, L2 caches. Means things are cached in this. So for easier understanding, I have drawn only one cache. Depending upon the size of this cache memory, things are cached in the cache memory. Just a minute, I have to take this call. उनसे ले लें, हमारे पास कोड नहीं। उनको नहीं मिल रहा भाई, वो तो बैकअप है। Now, Brijendra, pay attention. Everybody should pay
Yes,
attention.
yes, sir.
So, CPU actually cannot access anything from main memory. This is clear to you or not? So, if
Yes, sir.
CPU want to access anything, that has to be there in cache. Fine. So, this you have already studied in computer organization, cache memory. Anybody can answer whether they have studied this or not. I'm just reminding you. Direct mapping, associative, set associative. You guys remember this or not? Abhiraj?
Uh, Sir, we know about the cache and the main memory, but that mapping part we don't know.
So which portion of main memory, which block of main memory is going to be mapped to which block of cache? Fine. These are the three techniques: direct mapping, associative, and set associative. Got the point?
Yes, sir.
So you have to know all these things. This is important. Fine. So what is happening? That's what is interesting stuff. That if you remember your program counter, if it is of 32 bits, so it can address 2 to the power 32 locations of main memory. If your cache is always smaller than main memory, so you need to have some mapping mechanism that which block of main memory is going to be mapped to which block of cache. And that is what, so in from this address, 32 bit address, some bits are going to be utilized, which are going to work as an index to this cache memory. Remember, Vijendra?
Yes, sir. Yes, sir. Remember.
Now see how critical things are. Now see how critical things are. And people don't know this thing actually. And this 32 bit, which is not written in the books, this 32 bit which CPU is generating is actually logical address. Okay? So first of all,
Yes, sir.
logical address, whatever logical address is getting generated, has to be converted into physical address. Fine? Means where in main memory. Okay? And then
Yes, sir.
this physical address, some bits of this physical address, pay attention, are going to be used to find the cache block. where from CPU can access. Are you getting the point?
Yes, sir.
I'm again telling, fine. I'm again telling, pay attention. So CPU generates logical, which is going to be converted using address translation maps. That's a memory management module's duty of operating system. It is going to be converted into physical address, its actual address in main memory. But the sad part is CPU cannot access main memory directly. So this physical address where it is mapped, if it is not available in cache, then it is termed as, Abhiraj, remember, cache miss. Okay?
Yes, sir.
Then you bring back that particular main memory block into cache. Fine. But where in cache? There are many blocks. So that is the mapping technique, that which main memory block would be mapped to which cache block. So using some bits of this physical address, the cache block will be accessed. This is the whole process. But there is one thing which is missed here. Now, if CPU generates a logical address, Vijay's answer, and
Yes, sir.
if you convert that logical into physical main memory address, if you go to main memory and you find there is nothing, you know the physical address, but when you, first of all, the things has to be there in main memory, you need to check कि
Yes, sir.
जो एड्रेस हमने जनरेट किया है वो मेन मेमोरी में है कि नहीं, वो डेटा अब मेन मेमोरी गया, वो है ही नहीं, अब कहाँ से लाएंगे?
तो पेज फॉल्ट हो गया सर वो।
हाँ, फिर कहाँ से लाएंगे?
सेकेंडरी मेमोरी से लाना पड़ेगा।
कहाँ से? सेकेंडरी मेमोरी से।
एक्चुअली में सर पेज टेबल में ये प्रोसेस का वो बना के रखता है कि
नो,
Virtual
प्रोसेस
memory.
को
वर्चुअल मेमोरी इज दिस लॉजिकल मेमोरी, लॉजिकल एड्रेस। यही सब कंफ्यूजन है जो वहां पे कंपनी वाला आएगा माइक्रोसॉफ्ट का और VMware का, वहां सब गिर जाओगे। सेकेंडरी मेमोरी का एड्रेस वर्चुअल एड्रेस नहीं होता है, ठीक? वर्चुअल एड्रेस कहीं नहीं होता है। वर्चुअल एड्रेस
वहाँ पे कुछ
डिपेंड
नहीं
करता
होता
है कि तुम्हारा 64 बिट मशीन है या 32 बिट मशीन है। ओके?
है। यस सर।
और एक हार्डवेयर चाहिए होता है जो कन्वर्ट करेगा वर्चुअल एड्रेस इनटू फिजिकल एड्रेस, ठीक? V2P। तो अगर एड्रेस को कन्वर्ट करना है तो यहाँ पे रजिस्टर होना चाहिए। उस रजिस्टर का साइज डिसाइड करता है कि वर्चुअल मेमोरी का साइज कितना है हमारा। गॉट द पॉइंट?
यस सर।
So virtual address is nowhere. We require another thing also, where we can have a map to have mapping between virtual address to hard disk address. Got the point, Vijendra?
यस सर।
तो एक बार फिर से बता रहा हूं, ध्यान से सुनिए, यही पूरी कहानी हमको पढ़नी है। CPU generates logical address. Fine. Because when we compile a program, when program is compiled from high level to low level, we require some addresses, and these addresses are known as virtual address. This is known as compile time address binding. Fine. So you can compile a program anywhere else, generate .obj file, and then you can link the libraries, you can generate a exe file, fine, anywhere else, and that exe can run if your operating system and architecture are compatible on anywhere else. Is it okay? Okay, Vijan?
Yes, sir. Yes, sir.
So you can, and that's how you install a program, no? So you install a package by this. So the exe is generated somewhere else. So addresses are not fixed, that where actually the code will run in main memory. Those are virtual addresses. And when you compile a program, whole from 0 to 4 GB, virtual addresses are present. Fine.
Yes, sir.
Okay. So you have addresses at the compile time, and those are virtual addresses. Okay. And we have seen this thing that different program can have same virtual address, first or second lecture. Karimullah, remember we had a discussion on this?
Yes, sir.
Then I've told you something else also. Fine.
Yes, Lar and Pi.
Okay. Fine. So exe, and then you can run it here. So this is compile time address minding. So finally, when this logical address is nowhere, so this logical address has to be translated, fine, has to have a translation at two places. One where it is in main memory, where this logical address can be mapped in main memory, and where it is in hard disk. Okay, Vijay?
Yes, sir. Yes, sir.
So there has to be a provision to map this logical address into hard disk address. And then this is how we do the things. So the page fault you were talking about, the first thing is to bring that page back. Okay.
Yes,
So
sir.
in a hard disk, where is that page? Somebody has to tell that, no?
Yes, yes, sir.
From where to bring that page from hard disk. Okay. So you get the main memory address, physical address. This is main memory actual physical address. Then using that physical address, you get the cache block. And then CPU can access data or instruction. Is it okay to everybody now?
Yes, sir.
Okay to everybody? Think over it. Think over it for 2-3 minutes. Okay. If this is clear, then we can move ahead. So that's what I was telling you about compile time versus execution time address binding. Now, the another interesting thing is memory allocation. How to allocate memory? Because some processes would be big, some processes would be small. How to allocate the memory? Fine. Kernel tries to find contiguous portion of physical memory, also known as whole, to accommodate the new process. And if we do like this, contiguous allocation, then holes of various sizes after some time would be scattered throughout memory. When a process will arrive, allocate memory from a hole large enough to accommodate it. An operating system has to maintain information about allocated partition and free partitions. So this is, suppose this is the situation, process 5, 8 and 2 are there. Suppose process 8 went out, went to hard disk. So this particular thing is vacant. Then process 9 came. Then process 10 came, so on and so forth. Now, depending upon this, there are various algorithms in contiguous allocation. That there would be many holes, many free partitions. So where to allocate a arriving process? That is so there is first fit algorithm. Allocate the first hole. There should be list of vacant partition, non-allocated partitions. Allocate the first hole that is big enough. That is first fit algorithm. Under the best fit means you have to search the entire list and then search the smallest hole which is big enough to accommodate this. And this is going to produce the smallest leftover hole. This is like some more work you have to do. And then another is the worst fit. Allocate the largest hole which can accommodate. Here also you have to search the entire list, which is going to produce the largest leftover hole. रूपेश क्लास में अभी Fine. In both best fit and worst fit, you have to search the entire list. In best fit, you will be allocating the smallest hole that is big enough. In worst fit, you have to allocate you will be allocating the largest hole. In best fit, it will be producing the smallest leftover, whereas conversely, in worst fit, it would be producing the largest leftover hole. Now, what they have found out that first fit and best fit are better than worst fit in terms of speed and storage utilization. Fine. So this is the problem of contiguous allocation. What are the problems? That is external fragmentation. So there are small holes all throughout the memory. So suppose there is a hole of 2 GB, 2 MB, 6 MB, and 8 MB. And then there is a process arriving which is 10 MB. So if you can somehow join all these holes, the 10 MB process may be allocated. But the problem is this 10 MB memory is not contiguous. Free memory is there, but 10 MB process may not be allocated. So this is a problem of external fragmentation. Now, what is internal fragmentation? Allocated memory may be slightly larger than the requested memory. Now this is problem. So एक छोटा सा hole है, hole पड़ा हुआ है, but the process which is arriving is slightly smaller than that. So whatever leftover would be there would be useless. Fine. The size difference in memory internal to partition, but not being used. So you can reduce external fragmentation by compaction. It is again a time-taking task. So operating system has to shuffle the memory contents up and below to compact the memory. Fine. Place all free memory together in one large block. Compaction is possible only if relocation is dynamic and is done at the execution time. So this is again issues in contiguous allocation, fragmentation, and in external and internal fragmentation. But contiguous allocation is easier. The translation, translation from logical address to physical address is easy. What OS has to do? OS has to maintain the starting physical address or base and the size of the memory image or limit. There has to be a relocation register, fine, which is going to give you the base. There is a limit register, fine, and then you can get the memory. Contiguous allocation had the benefit of simplicity, but rarely used in modern OS due to fragmentation. So logical address is created. You see the limit register. If it is less than that, okay. Then you use a relocation register, which will give you the base. And then you add the logical address, you get the physical address. Fine. So it is just like relative addressing mode, if you remember. So what is happening? So suppose there is a memory which base address is 1000 and this size of this is 1000 to 1500, a logical address comes, say 700 is a logical address. Logical address will come. You'll check the limit. Limit right now is 500. No, it is greater than that. It is error for this whole. If it is, suppose logical address is say 300, you say the limit is 500. No, it's less than that. Then it will be added with what is the base? Base is 1000. So 1000 plus 300 equal to 1300. So 1300 would be the physical address of this 300. So in this way, we can get the physical address using the base and limit register, relocation register and limit register. This is easier to implement, simple, but it suffers from fragmentation problem. To avoid this, this is the most common technique which is utilized by majority of the architecture, and different flavors of paging are available, utilized by majority of operating system and computer architecture. And please be with me to understand it. Logical address space of a process can be non-contiguous. This is the first agreement. So process is allocated physical memory whenever possible, wherever possible, whenever available. It's not like that the whole process should be contiguously allocated in one memory partition. Divide physical memory into fixed size blocks, which are known as frames. Divide logical memory into blocks of same size, pages. So your logical address space and physical address space both are divided into equal size blocks. Physical memory blocks are known as frames, and logical memory blocks of same size are known as pages. Keep track of all the free frames. To run a program of size n pages, find n free frames anywhere and load the program. And set up a page table to translate logical to physical address. So what is going to happen is like this. CPU will generate logical address of say n bits. Suppose the page size and frame size, whatever is the page size and whatever is the frame size, can be represented by d bits. So within this logical address, this would be the d, and this p will be n minus d. So what is going to happen? Suppose this is your virtual address space. So this is 0, 1, 2, 3, 4 addresses, and then it is divided into some equal size pages. So this is a, suppose physical address space is divided into equal size frames. Now which page will map to which frame is decided by a page table. When CPU generates a logical address, depending upon the size of page, suppose size of the page is say 8 words. Fine. So D would be 3, something like that. Depending upon the size of the page, you'll be getting these bits. And remaining bits will work as an index into this page table. You go to that particular entry, and in this entry, the frame would be found. This entry, frame number would be found. Using that frame number and this displacement D, we can go into the main memory address. CPU generates a logical address. Depending upon the size of the page and frame, the D bits will be formed. Remaining P bits, which is N minus D, N is the complete logical address bits. Index into page table, get the frame number, frame number plus displacement, you can get the main memory address. This is how the paging is done at a very abstract level. Let's see. A page table of a process maintains mapping from logical page number to physical frame numbers. The operating system maintains a separate page table for every process it creates. When a process is created, a page table of that process is also created. Using this, external fragmentation is completely eliminated because any free frame can be allocated to any process. Internal fragmentation is going to be there because the last page of a process may be not completely equal to the page size. So last page being partially filled. So little bit of internal fragmentation is there. So operating system maintains a separate page table for every process. Salient features of paging: clean separation between logical address and physical address. Compiler can assign addresses to code and data. No worries that where program will finally reside in memory. Sharing of memory between processes is easier. And that is how kernel code was shared. Remember, Brijendra? Because we have only one copy
Yes, sir.
of kernel in main memory. So how the lower part of virtual address space of every process would point to the same main memory address. That is how we have done that. Two logical pages can point to same physical frame in the page table. And that is how a kernel code can be shared, or any reentrant code can be shared. Obviously, there is additional overhead of address translation. Address generated by CPU is divided into page number P, used as an index into page table, which contains base address of each page in physical memory, or the frame number. Page offset D combined with the base address to define the physical memory address that is finally going to be sent to the memory unit. The page number is mapped to physical frame number by looking up the page table of that process. And then physical address is obtained from physical frame number and the offset within the frame. We'll take one example, don't worry. Like this. OS maintains page tables during the life cycle of a process. Program control, process control block contains a pointer to this page table. This pointer is also maintained in a special CPU register CR3 in x86 and updated during context switches. So जब नई प्रोसेस आती है, उसकी पीसीबी से पेज टेबल का एड्रेस निकालते हैं और ये सीपीयू रजिस्टर को अपडेट करते हैं जब कॉन्टेक्स्ट स्विच होता है. बात समझ में आई? And then
Yes,
memory management unit hardware uses this page table to translate logical address requested by CPU to physical address. CPU generates logical address. This D is the page size. Fine. Using page number index into page table, get the frame number or base address of the frame, add D into this, you get the physical address. This is how translation from logical address to physical address is done using paging. Efficiency. Every data instruction access requires two memory access. पहला पेज टेबल के लिए मेमोरी एक्सेस करना है और फिर एक्चुअल डेटा इंस्ट्रक्शन के लिए. किसी भी चीज को ढूंढने के लिए फर्स्ट यू नीड टू एक्सेस द पेज टेबल. अब पेज टेबल को कहाँ रखें? पेज टेबल क्योंकि बहुत बड़ी होगी, उसको सीपीयू रजिस्टर में नहीं रख सकते हैं, तो पेज टेबल भी मेन मेमोरी में होती है. तो कुछ भी एक्सेस करने के लिए फर्स्ट ऑफ ऑल यू नीड टू एक्सेस द पेज टेबल. फ्रॉम दैट पेज टेबल यू नीड टू you will get the frame, and then from frame add the displacement and you can get the actual memory address. To avoid this dual access for every data instruction, we can have translation look aside buffers or associated memory, which are also known as TLBs. So what is, it's just like a cache of a page table. So there what is happening, whole page number will be parallelly, सपोज 16 एंट्री का एक टीएलबी बना लिया. पेज टेबल में तो बहुत सारी एंट्रीज है. तो पहले पेज टेबल कहाँ गया, पेज नंबर कहाँ गया, पैरेलली सबसे कंपेयर हुआ टीएलबी में. अगर मिल गया, टीएलबी हिट हो गई, तो ये इसको हम फास्ट मेमोरी या कैश में कहीं बना सकते हैं. स्पेशल मेमोरी, fine, which is faster. Associated memory is costly because you need to do parallel, you have to have parallel comparators. Fine. So page number will be parallelly compared with all the page numbers in the TLB. If hit is there, you get the frame number, add the displacement, get the physical address. Otherwise, if miss is there, you have to follow the whole process. Go to the page table, get the frame number, add the displacement, get the physical memory address. So this can be improved. Suppose associative lookup takes some silent time unit. Assume memory cycle time is 1 microsecond. What is the hit ratio, percentage of time that a page number is found in the associative register? Suppose hit ratio is alpha, you can find out the effective access time. Effective access time would be what? Hit ratio 1 plus sigma, fine. Associative lookup is sigma time unit plus 2 plus sigma 1 minus alpha. If hit is there, fine. If hit is there, then you have to access memory, fine, and TLB. If miss is there, you have to access memory twice and TLB तो कब पहले करना ही पड़ेगा. TLB ही देखेंगे तभी मिस पता चलेगा. मिस हुआ तो TLB टाइम चला गया. फिर एक बार मेमोरी पेज टेबल के लिए, दूसरी बार मेमोरी एक्चुअल मेमोरी के लिए, and then finally you'll get this effective access time when you are using TLBs. Fine. Anybody want to ask anything here?
So why are we using TLB once again?
Why we are using TLBs once again? Because we want to avoid this main memory access.
So where are TLB? In the main memory, or where is the TLB stored?
That can be anywhere. That depends upon the implementation. Because that is associative memory. It's a spatial memory hardware. Okay.
Okay, so different from main memory.
This is different from main memory. Fine. So, do you understand the meaning of L1, L2 caches?
Not exactly.
So you need to go through that and then just have it, Google it and look about and see about, because in cache also we use associative and set associative. The mapping, I told you, no? Cache to main memory mapping, there is a associative and set associative. So this is a cache memory technology actually. Why any memory is associative memory? That is again an interesting thing. Look, generally you give address to search something. Yes or no? You are using page number to search the page. Yes?
Yes, sir.
Fine. This page number is getting utilized. and then you are using address to search the memory content. Okay, so this is